So, first of all, I guess I'll try and stand, and then when I get tired, I'll sit. I want to thank Enzo and Enrico and all the organizers for having me back once again. It's an incredible pleasure and honor every time to come, and as Enzo said, I've come several times, so it's really wonderful. Thank you. So I'll be talking today. Before I start, let me emphasize again. Please feel free to interrupt with questions. As Enzo said, they shouldn't be very hard, long, substantive questions, at least during the lecture. But if there are clarificatory questions or something that I could probably answer in a few sentences, then please speak up. But if you have like a really urgent, burning, very deep, hard question, you can raise it, and then I'll keep it in mind until we get to discussion at the end of the session. And please, please, please do not be afraid to ask questions. I guarantee you, if you have a question, at least 1/3 of the rest of the people in the room have the same question and aren't asking it. And another third probably should have the question but haven't yet thought of it. And you will be doing everyone a favor by asking the question. And as I like to say, there are no stupid questions, only stupid people who ask questions. No, wait, I'm sorry, that's okay, no, I'll try and get serious now, which is hard for me. So I'll be talking today about the epistemology of quantum gravity, but the morning lecture will almost entirely actually be about epistemology of physical theories, since this is a summer school on epistemology, and epistemology in particular of, in my view, the single most problematic branch of physics. I think it's worth spending some time talking about what exactly it is to have a theory under what I call epistemic control. And so I think I'll just dive right in, and you'll see what I mean by that as we go. Those of you who know me know I can never resist beginning lectures with a passage or a quotation from someone I admire or that I think is particularly relevant. And so I am going to indulge myself yet again. And this is from a poem by a very great early 20th century American poet, Wallace Stevens, one of my favorite poets, 13 Ways of Looking at a Blackbird. If you're not familiar with this poem, I could not more strongly urge you to go read it pretty much right now. It's better than this lecture will be, for sure. And more important than this lecture will be, for sure. So if you want to, just leave the room and go read the poem. I will not be insulted. But so the poem is broken up into 13 sections. This is section 8. I know noble accents and lucid, inescapable rhythms, but I know too that the blackbird is involved in what I know. It may not be obvious to you yet what, why, and how that is relevant to our topic, but as you will see during the course of the lecture, the blackbird is deeply involved in everything that we know in physics, and philosophers almost always ignore the blackbird. And if you read the rest of the poem, you'll see what I mean. And I'm going to be especially indulgent today and indulge in yet another quotation from one of my heroes. This is someone I hope everyone in the room will recognize as someone deserving of a place in this lecture, if you weren't so crazy about Wallace Stevens. James Clerk Maxwell, not only probably the third greatest physicist who ever lived, but in my mind, the most philosophically sophisticated physicist who ever lived. So in 1870, he was giving an address to the mathematical and physics sections of the British Association. He was president of the association. He says, "We are met as cultivators of mathematics and physics. In our daily work, we are led up to questions the same in kind with those of metaphysics, and we approach them not trusting to the native penetrating power of our own minds, but trained by a long continued adjustment of our modes of thought to the facts of external nature." I want you to pay particular attention to the last clause, last two clauses. not trusting to the native penetrating power of our own minds, but trained by a long continued adjustment of our modes of thought to the facts of external nature. Because almost every single problematic aspect of quantum gravity reduces to the fact that in this area of physics, our minds have not been trained by a long continued adjustment of our modes of thought to the facts of external nature, because we know no facts of external nature about quantum gravity. We have no experimental or observational evidence, no empirical access to anything that we think of as being a quantum gravitational effect. And I'm going to be really indulgent and have one more quotation. So this one, again, someone I hope everyone in this room will recognize as someone who perhaps should be listened to on these matters, Francis Bacon from his Novum Organum, Book 1, Aphorism 10. The subtlety of nature far exceeds the subtlety of sense and intellect, so that these fine meditations and speculations and reasonings of men are a sort of insanity, only there is no one at hand to remark it. Well, today I am here to remark it. So, the outline for the lecture, I'll say a few things just to set the scene. I'll tell you what I mean by empirical epistemic control. I will spend some time going through two of the conditions of what I think, there are several conditions I claim for having epistemic control over a theory. Two of the most important ones are what I call having an empirical rendition and understanding the breakdown scales and the regime of applicability of the theory. I'll then tell you why we care about epistemology and should not care very much about metaphysics. Although you can't avoid it, but you can minimize it. It's like I won't go there. Okay, I'll then actually get to the quantum gravity part of the talk. And I probably won't make it through the entire lecture this morning, so some of it we'll pick up this afternoon. Okay. So, again, those of you who know me know that I can sometimes be rather contrary, crotchety, and cranky about things that I don't like very much. But even for me, I think I'm going to be pretty contrary, crotchety, and cranky today about quantum gravity. And I'm going to do this partly because most physicists themselves just won't do it. And I think most philosophers defer far too much to the physicists on these matters. But it needs doing, because many physicists in their public pronouncements and in their private work habits, and their not just private, meaning alone in an office with pen and pencil, but in collaboration with colleagues, the way when you press them, they will sometimes, usually grudgingly, but they may, if you press them enough, they may sometimes be forced to admit that we have no empirical evidence for quantum gravity. We really don't know very much about it, and it's not even clear what it is or should or can be. But this is never said almost never said in public, almost never said even amongst friends and colleagues, but it is desperately, desperately important to keep in mind if we're going to understand this area of alleged physics. Eugenia just left the room. Too bad. So I'm very pleased about my fellow speakers. So Eugenia, who just left the room, is a physicist who works in overlap of several programs in quantum gravity, and I really admire her. She's really quite contemplative, which one wants in a physicist, and she really is one of the rare physicists who does question and constructively criticize, and is very happy to discuss the foundational, the epistemological, the methodological, the conceptual, all the deep problems of quantum gravity. So I'm thrilled she's here. Karen, who is also not here, I think she's arriving this morning, is saucy. She's which is one of the finest traits for a philosopher, in all seriousness. She will be, I think, skeptical and critical, just knowing her, but probably won't go as far as I would like in that direction. But mostly I'm going to be really contrary, crotchety, and cranky because Richard, who is our last speaker, who usually feels quite triumphant about string theory, but whether it's justified or not is another matter. Because Richard, I suspect, just knowing Richard, is going to be as supportive, constructive, and sunny as is humanly possible, because that's just how Richard is. He's basically the nicest guy on the planet. He's just a total sweetheart, and he couldn't be contrary, crotchety, or cranky to save his life. It's just not in him. And so I need to redress this balance also. And this is actually a good object lesson, I think, for younger people in the audience. So Richard is a very dear friend of mine. And the lesson is that one can like someone tremendously, like them with respect, affection, admiration, think they're an excellent philosopher or physicist, have fabulously constructive and edifying conversations with them, learn a tremendous amount from them, and yet still think they are as wrong as eating spaghetti with a spoon. And that's how Richard and I are. Richard and I disagree on everything. But I always learn more from talking with Richard than I ever learn from talking with someone I agree with. So find people with whom you disagree, but whom you like and respect and can learn things from, and talk with them constructively. It's the best way to learn. Okay, enough kind of preaching and bad jokes. Well, probably not enough bad jokes, but we'll get to this. So physicists in some areas of physics and philosophers in essentially every area of philosophy promulgate theories for which we have no principled, cogent understanding at all of their representational and evidential relations with the real world. I'm going to be talking about physics today, but most of what I say actually translates almost verbatim to the epistemology of philosophical theories. Theories of scientific representation, theories of scientific semantics, theories of ethics. Philosophers by and large, have total lack of epistemic control over almost everything they talk about. And it's really a scandal. But I'm not going to be talking about that today. But I will say that, so much philosophical blood, toil, tears, sweat, and ink has been spilled, suffered, shed, secreted, and wasted for the past, 2,500 years or so in the attempt to understand what the empirical content of a scientific theory is. I think the first serious attempt we have in the Western world in this regard was Plato's Timaeus. And then there's a representative sample of, I just chose one representative from every decade starting in the 20th century up to today. Clearly the last item in the list is the most important. But even though so much work has gone into trying to spell out, trying to understand what the empirical content of a physical theory is, so some philosophers will say, well, we need to give a formal semantics for the formalism of the theory. That tells us the empirical content. That's something that Carnap or von Frosten would say. Or someone would say we need to understand the constitutive a priori, the relativized a priori, to understand the empirical content. That's what Reichenbach would say. But little attention has been paid to the epistemic conditions that are required to have confidence that we can, in fact, fruitfully play with, use, apply, extend theories so as to further the enterprise of science. Which is to say, to have confidence that, at a minimum, what we think of as the empirical content is, in fact, rightly conceived of as such. And moreover, that we understand how to extend our theoretical knowledge of the world based on that empirical content into physically significant application of the theory to the world. And that, indeed, when that is the case, gives us the strongest evidence that we've got the empirical content of the theory right and otherwise have the theory under adequate control. Contrary to popular belief, for instance, to understand the empirical content of a theory on popular philosophical construals is not eo ipso to understand possible evidential relations between world and theory. But those evidential relations form the heart of the epistemology of science. You have to understand what can count as evidence, how you can acquire it, how you judge it, how you evaluate it, how you apply it. But on any traditional, popular construal of what knowing the empirical content of a theory is, that is never enough to allow you to understand what the possible evidential relations between the world and the theory are. One has to know a lot more than what the empirical content of a theory given by philosophers gives you to understand that. And that's the primary motivation for what I'll be talking about today, is to understand what further one needs in order to get control over that. So broadly and crudely speaking, what I call epistemic control, there are three categories of conditions. The empirical or the experimental, the evidential or the epistemological, and the theoretical or methodological. And I'm a little hesitant about this classification. I'm always hesitant and a little leery of classifications because it's quite common in philosophy to try and analyze something, and analyzing something, very often takes the form of trying to find a set of concepts or categories that you can use to divide the things up in whatever set of objects or entities or whatever it is that you're interested in. And that can be very useful when it's that can be very useful to have when it's a good classification. But all too often, I think we end up trying to find classificatory systems just for the sake of having a classification by itself. And in this case, because the idea of epistemic control is really quite long and complex and unwieldy, I'm introducing the classification in the attempt to, I hope, make it somewhat easier to digest and keep all the different moving parts in mind. I'm not entirely happy with it because I think that there are some misleading connotations in the rubrics I'm using for the categories, and many of the conditions don't easily fit under one category. But I think the risk is worth the gain in any event. I hope it is. So, epistemic control consists in having an understanding, to some degree, of some non-trivial subset of the following. One must have an empirical rendition. I'm going to explain all of these in more detail as we go very soon. I'll say very briefly right now, to have an empirical rendition is something like to know how it is that the theory can make contact with empirical data. One needs to understand what the evidential warrant for the theory is or can or should be. One has to understand why the theory is needed in the first place. One has to understand the regime of applicability, the set of physical systems, let's say, that the theory is meaningfully, appropriately, and adequately applied to treat. So, for instance, Navier-Stokes theory, the classical theory of viscoelastic thermoconductive fluids, treats the water in this bottle extremely well when I'm just holding it more or less still, or even when I'm shaking it a little bit. But if I start shaking it a lot, so it becomes turbulent, Navier-Stokes can't handle that. Navier-Stokes breaks down in its representation of the system. It gives bad results. So right now, the water is in the regime of applicability of Navier-Stokes. Now it's not. And the breakdown scales are measures of the values of quantities that tell you when you're approaching the boundary of the regime of applicability. So, for instance, in the case of turbulence, it might be some measure of a characteristic kinetic energy over a characteristic viscosity coefficient. That ratio, when that ratio approaches a certain value, then you know that Navier-Stokes is going to break down. I think it's more standard to think of breakdown scales as being energetic or spatial or temporal. So, Navier-Stokes also breaks down if you try and make measurements a couple of orders of magnitude larger than the mean free path of the molecules of the water. Because like Navier-Stokes is a classical continuum theory. It treats the fluid as a continuum, but we think that the water is actually really made up of something like discrete molecules. And as soon as you start making measurements that where the effects of that discreteness begin to manifest themselves, then Navier-Stokes breaks down. But the breakdown scale, but as I just mentioned with the example of turbulence, breakdown scales occur for essentially every kind of quantity that a theory attributes to a system in many, many different combinations and ways. And as we'll see when we talk about it later, breakdown scales sometimes depend on quantities and systems that aren't even representable in the theory.
Going through this category, so I was just wondering if there are some clear boundary conditions for understanding at all. If there's zero understanding, let's say, like so, and 100% understanding in your theory, where this is all fitted in between.
And that's a great question. And I will say something about that in a few minutes.
Right.
But if I don't say enough, then please, or if you have a further question about it, please speak up again. So you have to know the asymptotics of various quantities and dynamics in the system, and this may sound a little strange, especially to a philosopher who doesn't tend to think about these kinds of things. But if you don't understand the asymptotics, then you really have no way of trying to understand the next item in the list, what approximations and idealizations are justified. Because almost all approximations and idealizations depend on taking the value of some quantity as it goes to infinity, or if it goes to zero, or you take some asymptotic limit of something or other to simplify the system. Almost all approximations and idealizations depend on that. So you really have to understand the asymptotics of the quantities and dynamics of the theory. And that, as I say, and we need to understand what approximations and idealizations are justified, because the world is just too complex a place for us to construct an exact, perfectly accurate model of the water in this bottle. It's just, I could easily talk for a good 15 minutes, I think, about all the shit happening in this water right now. It's a really, really, really complex system, even though we normally don't think of it as such. So we approximate and we idealize and we simplify until we come up with something that's conceptually and mathematically tractable, and we solve it. We solve whatever equations or model we get, and miraculously it works incredibly, incredibly well, even after we've approximated and idealized and simplified almost everything away. That really is miraculous. That is the miracle of science. That our almost recklessly, childishly simple theories and models give us such incredibly good results for what, when you really begin to think about it, are mind-bogglingly complex systems. You have to understand which quantities and types of dynamical evolutions are detectable through coupling with the environment, because you need to build instruments to examine them and measure them, and to do that you need to have some confidence that your instruments are actually interacting with and coupling with the system in ways you understand. You have to know how to schematize the observer, which roughly means you have to know how to build a theoretical model of an experiment or an experimental instrument in its interaction with the system. You have to understand what legitimate forms of argumentation are in the theory. This is a little bit of a tricky one. What I mean by this, I'll give you a simple example. Perturbative analysis is ubiquitous in physics. When you can't solve something exactly, it's incredibly common to expand the expression for some quantity or structure in, say, a Taylor series, and truncate after some finite order and just use the first n terms in your expansion. And that works very well in many, many cases. But for instance, in Newtonian gravity, the most common form of that kind of perturbative analysis that was used until the end of the 19th century worked great for first order terms and second order terms. Poincare discovered it didn't work for third order terms. So that's the kind of, so if you want to use that kind of perturbative analysis in Newtonian gravity, you have to be sure to not be dealing with a regime in which third order effects are relevant. So that's the kind, so any form of argument that depends on a perturbative analysis for a system in which third order effects in the relevant perturbative scheme manifest themselves is not a legitimate form of argument in Newtonian gravitational theory. You have to understand what the physical significance and the physicality of various parts of your formalism are. So in general relativity, one form, a cotangent vector at a point may represent the vector potential of an electromagnetic field, but it may also represent the kind of, if you like, potential for a killing field, for a symmetry of the metric. If you take the antisymmetric derivative of your one form, then I won't go into that. But the same mathematical structures in your theory can have many, many different physical interpretations, can have many different physical significances. And the physical significance, the physicality of a vector field that represents a symmetry of the metric in general relativity is very different than the physical significance or physicality of a vector field that represents the vector potential of an electromagnetic field, even though they may in fact be, in some space-times, one and the same vector field. You have to know what it may take to give an interpretation of the theory. Most of the time, that's not very hard, or at least relatively speaking. For quantum mechanics, that is obviously infamously hard. You have to understand when your theory itself has enough evidential warrant that you can now begin to use it as evidence for other claims. So that's evidential warrant 4, number 2, evidential warrant for the theory. 4 evidential warrant, number 12, when you can use the theory for evidential warrant for other claims. You have to understand its relation to other theories, and not just, for instance, you of course have to understand its relation to theories of measuring instruments. So you almost always need to understand its relation to various theories of solid state physics, of perhaps fluid physics or plasma physics, or QED or something, depending on what your measuring instruments are. But you very often have to understand its relation, so to speak, to prior and posterior theories. So it's incredibly important to understand the relationship between Newtonian gravitational theory and general relativity. For instance, one among many, many reasons, and a very important one. If you actually look at the evidence that most astrophysicists and cosmologists use when they are trying to test or understand the relation of their theory to empirical data we've actually collected, 99% of the data was collected, structured, and is presented using Newtonian gravitational theory, even when it's being used to test general relativity. It's a very odd situation. You use a theory that believe, is the worse, higher level, shallower theory, the theory we know is not correct, to collect, structure, and manipulate data in order to compare it to the predictions of the better theory. And the main reason we do it is because Newtonian gravity is in certain respects so much easier than general relativity that it would simply be impossible for us to do what we want to do if we really made ourselves use general relativity the entire way through the evidential argumentative process. But we have good faith that what we're doing is legitimate because we understand when, where, and why, and how certain general relativistic effects and phenomena can be reduced to a Newtonian treatment because we understand the relationship between the two theories, I think very, very well. But you also need to understand, well, there are other examples, but I've already probably spent too much time on that. You have to understand relations among different formulations of the theory. Every single physical theory has many, many different formulations. I actually have a hobby of collecting formulations of GR, which probably bespeaks an impoverished fantasy life, but it's fun. It keeps me busy during the cold, rainy afternoons in Munich. At last count, I think I have 37 different formulations of GR. And some of them are really radically different from each other. And very radically different from the standard, manifold plus metric plus stress energy tensor formulation that if you've learned GR at all, which I hope you've learned some, is probably what you learned. You have to understand how it is, why it is, that these really radically different formal structures seem to latch on to the same parts of the physical world and return the same results. And finally, you have to understand various categorical or foundational concepts and issues that the theory raises. Things that aren't strictly determined by anything empirical or purely theoretical that we have. So for instance, the age-old question, is this theory deterministic? Well, after a long time of some truly brilliant and amazing analysis, philosophers and physicists have come up with dozens and dozens and dozens of different definitions of determinism, and trying to figure out whether a theory is deterministic or not in any of those senses is arguably an important thing to figure out. But it's something that really you can't, I think, attack until one has an enormous amount of understanding about almost everything else in the theory. And very roughly speaking, satisfaction of each condition is necessary to satisfy everyone below it in the list.
I didn't understand 11. What it may take to give you just said.
Yeah, because talking about interpretation, totally fair. I did not say very much about it. So, what it may take to give an interpretation of a theory. So, in most cases, giving an interpretation of a theory, both philosophers and physicists disagree about what it may mean to give an interpretation of a theory. And I can think off the top of my head of at least 3 different senses of what that may mean. And so for the purposes here, what it may take to give an interpretation of a theory is essentially, I think it's fair to think of it as more or less the culmination of everything above it plus 15. But there's a lot more to say about it. But it's not going to be relevant to almost anything I'm going to say in this lecture, although it is relevant for trying to understand quantum gravity in general. Because if we don't know how to interpret quantum mechanics, we're not going to know how to interpret quantum gravity. So to give an interpretation I'm floundering here because I can either just talk for an hour about it, or I can say something really confusing and crappy about it in 30 seconds. So I'll say something really confusing and crappy about it in 30 seconds. It's essentially.
Just give me an example, one example, right? What it takes, something takes what to give interpretation.
Okay. So I won't use quantum mechanics because I hope people have some idea of what the issue of giving an interpretation of quantum mechanics means. Let's take Newtonian particle mechanics. I think most people would probably not think it's difficult to give an interpretation of Newtonian particle mechanics. In fact, it's very difficult because if you really treat the particles as infinitesimal points, then it becomes extremely difficult to understand for instance, what one means by collision. It becomes incredibly difficult to attribute a mass to a particle in any mathematically sensible way. In fact, I would argue that we had no mathematically sensible way of doing that until at least the 1950s, when Laurent developed distribution theory. So to give an interpretation of Newtonian particle mechanics, you have to be able to say what the physical meaning of all the terms in the theories are. You have to be able to connect it with empirical results. But more importantly, you have to have confidence that there is no that there's no incoherence or lack of cogency in your understanding of the theory globally. And I don't think we actually had that for Newtonian particle mechanics until the 20th century, and we still largely don't have it, I think. there are other problematic aspects of it. Because, for instance, if you really, here's a fun problem for you. If you really want to try and give a mathematically cogent interpretation of Newtonian particle mechanics, and you allow distributions to represent masses, which you have to do, then why not allow distributions to represent forces? But if you allow distributions to represent forces, if you allow distributional forces, then it's an easy calculation to show that hitting if you impress a force on a particle that is the derivative of a Dirac delta distribution, your particle will move discontinuously in space. So then it becomes necessary to, if you want to give an interpretation of that, you have to say what you mean by, for instance, you have to be able to answer questions like, well, if this particle, when I hit it with this distributional force, jumps discontinuously in space, is it the same particle? You have to be able to answer questions like that to have an interpretation of the theory. I'm not familiar with that, but from the very little you've said about it, it sounds like I'd be sympathetic to it. I mean, I think realistically, I could probably move interpretation down to the last item on the list. Now that I'm talking and thinking more about it, I'm thinking maybe I should do that. Because it really, yeah, I mean, I think that one has to know an extraordinary amount about a theory to give an interpretation of it, and then it's not exactly clear what use the interpretation is, except to scratch the itch of your unhappy conscience, your unhappy intellectual conscience. So, a question to discuss over wine tonight. Okay, so in a little more detail, so the empirical rendition is you have to have some understanding of how the theory can make contact with empirical data that we have in hand or that we can foresee how to acquire in a way compatible with the experimental component of our current epistemic state. As I'll discuss later on, the closest analogs to this idea, when I give you more detail about it later in the lecture, would be something like a Reichenbachian coordinating principle or a Carnapian, God damn it, what's the word? I'm going senile, I can't remember these things anymore. So Reichenbach had his coordinating principles and correspondence rules. Carnap's, it could be like Carnap's correspondence rules, or Reichenbach's, contemporary philosophers talking about representational capacities. But there's a very important reason why I don't like those approaches as a way to make sense of the idea. Very briefly, and we'll discuss it more later, it's because we want to be able to allow a physicist to investigate, use, develop a theory when they don't yet have anything in hand remotely like a Reichenbachian coordinating principle or a Carnapian correspondence rule. Because that's the history of physics. And I'll discuss some examples of that as we go. Item 3, why is the theory needed? Well, there may be inexplicable experiments like Michelson-Morley, that was, at least according to some people, important for the development of special relativity. According to others, not. Nonetheless, a historically significant, inexplicable experimental result. There might be indirect empirical evidence that seems to require a new theory. So, the accelerating expansion of the universe, indirect evidence for dark matter. Dark energy. The flattened velocity curves of spiral rotation galaxies, indirect evidence for dark matter. There can be, you might need a theory to save an important physical principle. The theory of the neutrino was developed to save the principle of the conservation of momentum in scattering experiments. You might need it you might think you need it or want it for purely theoretical reasons or pragmatic reasons or aesthetic reasons or metaphysical commitments. But it's really important to understand what the motivation, what the urge, what the necessity is. That will guide you, it should guide you in downstream investigation and downstream application. So these I've talked about. Is there anything I want to say more? So this is, I think that the organizers will send the slides out to people. So a lot of the stuff that's on the slides I've said already. I'm not going to repeat, but they'll be there for you if you want to look at the slides later on. Yeah. Okay. So this is just a summary of all the conditions under their classificatory heading. So the empirical experimental conditions, the empirical rendition, why a theory is needed, the regime of applicability, the detectable coupling of quantities and evolution, schematization of the observer, physical significance, relations of the theories. Evidential epistemological is obviously evidential warrant for, why a theory is needed, when and why we can use the theory as evidential warrant for further downstream claims, what the relationship of the theory is to other theories. The theoretical methodological, again, why the theory is needed, asymptotics, approximations and idealizations, couplings, schematization, and so on. I will say that although I'm talking about theories in this lecture, everything I say about epistemic control actually can be applied almost unchanged to, if you like, a more granular structures like models in the theory. One has to understand almost all of these things to have control over when a model is a good model, when it's being rightly applied. And for most other structures and substructures in a theory as well, it makes sense to talk about whether or not or how much epistemic control we have over it. So as I said, roughly speaking, satisfaction of each condition in the original list, this one, is necessary to satisfy everyone below it, but the situation is really much more complex than that when one tries to examine it in finer detail. Because in practice, to acquire the ability to recognize the state of affairs that's required to satisfy the condition, and more importantly, to develop the epistemic capacity that's required in order to actually satisfy the condition, is almost always a dialectical process involving several different elements, several different conditions being applied and working in tandem at once. I think it's almost never the case that you make progress on developing epistemic control over one item on the list in complete isolation from all other conditions. So even though I say very roughly speaking, the items lower in the list items higher in the list are necessary to gain competence over items lower in the list. It's when you really dig down into the details and study, how things actually work, say in a historical example, things get very messy very quickly. And epistemic, control en bloc, all the conditions at once, itself comes in gradations. It's not a binary thing. It's not a yes or no. We have epistemic control or we don't. It makes most sense to talk about relative orderings, perhaps, or at least relative comparisons. We have more epistemic control over general relativity today than we did in the 1950s when we didn't really have a good understanding, say, of gravitational waves. And also, the satisfaction of every condition in the list itself comes in gradations. It's never an absolute yes or no thing. And I think it may happen, and moreover likely always does happen, that we will have achieved progress for different parts of a theory with respect to different conditions to different degrees. So we may have developed we may have developed a very deep understanding of how to schematize the observer, how to model experiments and observations, without yet nonetheless being able to use the theory as evidence for something else. That was pretty much the state of cosmology in the 1920s and 1930s. People understood their telescopes incredibly well, but cosmology was in such a piss-poor state for because of technological problems and some theoretical problems, that almost no one was willing to use claims about cosmology as claims for other things in cosmology that we didn't yet have empirical evidence for. They didn't think it was good enough. So the list is not intended to be exhaustive, merely exemplary. I do have hopes. I've captured most of the most important provisions, but I strongly suspect that there is, in fact, in principle, no complete, final canonical such iteration and explication of the provisions and conditions for having epistemic control, once and for all, applicable to every single theory. Although God knows most philosophers will want that, because most philosophers just can't abide the idea of not having the one true thing that we must understand in order to understand a thing. Goddamn Aristotelians. But I mean, as the nature of our theorizing evolves and novel forms of theory arise, probably novel conditions for epistemic control will relatively arise, and perhaps some existing ones will, fall by the wayside. If contemporary craze for gauge gravity dualities and holography, ever pan out, if they ever bear real fruit, what it would mean to have epistemic control over such a theory would almost certainly involve novel conditions, those that are required to control the duality itself, which are nothing like anything else in any physical theories we have that actually do make contact with empirical data and the real world. So I think one can always meaningfully talk about the epistemic control of individual researchers, but I think, and this is something that is speculative, but unfortunately really important for understanding quantum gravity. So I would love to hear people's thoughts on this. I think one can talk about a community having epistemic control only after the theory has achieved some degree of maturity, because there has to be some significant amount of consensus among the community on whether, how, and to what degree many, although perhaps not all, of the conditions are satisfied. And I think this has not yet happened for any subcommunity of quantum gravity. And if you want to see, a good example of that, just go to Penn State and try and get, Ashtekar and Bojewald into the same room. It's ugly. Or in strings, the same thing happens. And I mean, much less to have any kind of consensus among the wider community of quantum gravity researchers, working on all possible programs of quantum gravity. Okay, so before I discuss what is involved in having an empirical rendition, are there any questions?
I mean, one small question that
Yes.
came up now was when you were discussing what kind of novel bits would come to this list of 15 points in terms of epistemic control once we get the ADSF, CFD, and cosmology or something. What are ideas as to what that would be, how that would work?
So I'm sorry, I didn't quite follow. Are you asking me what my thoughts are?
Yes.
So what I think would be needed in order to, okay, so yeah, so I think that in this case, it would be something, at a minimum, it would be something that would be similar to this, but for one thing, we would have to, I mean, there's a mildly raging debate in the community itself and among the few philosophers who think about these things, about whether the two different sides of the duality, let's say for ADS CFT, the conformal field theory on quote unquote the boundary and the gravity theory and the bulk, whether those are simply different formulations of the same theory, or whether they really are theories of truly different physical systems that are in some sense truly different and yet in some sense truly the same, and trying to understand what exactly that means. They're truly different and yet truly the same.
This would need to be specified in 9, but overall, I mean,
It would, well, I think it would be something like 9. I mean, it may, depending on where you come down in the debate, it may just end up being 9. But I think there are other positions where it's going to look nothing like 9. So, and if one of those is what turns out to be the best way of thinking about these things, then I think we will need to try and understand what we need to understand in order to feel like we have control over such a theory.
I mean, it's interesting because in doing or in making that step, epistemic control itself kind of becomes this evolving model in some sense, or this evolving theory about theory. So
yeah, that's right.
You do a second order switch in there, which seems important to also consider in terms of what it is that we're trying to do.
No, I think I think that's exactly right, and I think that's a very important point to keep in mind. Okay. So as I said, it's the empirical rendition. Now, an empirical rendition of a theory is some understanding of how the theory can make contact with empirical data. It may be much less than a complete interpretation of the formalism. It may be much less than a thorough understanding of the physical significance of entities and structures of a formalism, and it may be much less than direct and decisive empirical support for the theory. It does require, at a minimum, to have some understanding of what direct connection to empirical data would be for the theory, and as I've already remarked, it will often consist of something much less than something like Carnapian correspondence rules or Reichenbachian coordinating principles or Tarski-Bet semantics or possible world semantics or analysis of representational capacities or anything else philosophers love. Because we want to be able to allow a physicist to meaningfully investigate a theory, both theoretically and experimentally, when much about it, including much of its epistemic and empirical content, is not yet known. And I'll discuss a couple of examples of that in a moment. But I will say before that I think that to have an empirical rendition is the one condition that actually is necessary for epistemic control. All the others you can do without for at least some period of time while you're getting your feet under you and trying to and getting the lay of the land. But if you don't understand how what you think of as your theory can possibly make contact with empirical data, you're not doing physics. Call me old-fashioned. I like empirical data. God, I wish Richard were here. I would really love to make fun of him to his face. So, yeah, I mean, the rest are individually important, but I really don't think you can have. And it's almost always going to be the case that you can't have an empirical rendition without satisfying some of the other conditions to at least some degree. But it's probably not going to be the same subset of other conditions in every case. So I really do think that the empirical rendition is the only one I'm willing to say is absolutely necessary. So a really beautiful, profound, extraordinary, groovy, sexy example, which I think philosophers really should pay more attention to and should work on more. It's an extraordinary episode in the history of science. Is Hertz's search for ways to produce and to measure electromagnetic waves based on what I think is manifestly a partial empirical rendition of Maxwell theory. So you may recall Maxwell published the final paper he published on the topic, a dynamical theory of the electromagnetic field, was 1864. He gave what we now know of as the Maxwell equations. He was already able to derive the wave equation from Maxwell equations in that paper. So he knew that at least some mathematical solutions to his theory were oscillatory in a particular sense, seemed to represent waves of electromagnetic intensity across space and through time. And that actually was one of the single most important seeming predictions of his theory. Because at the time, the main contender, very, very quickly after 1864, after the publication of that paper, Maxwell's theory became one of the two main contenders for a theory of that unified electricity and magnetism. The other one was Helmholtz's theory, which was an action at a distance theory. And you may know that in an action at a distance theory, such as Newtonian gravity, you can't have oscillatory solutions. There's no such thing as a Newtonian gravitational wave. And in Helmholtz's theory, which was action at a distance, there were no free electromagnetic oscillatory solutions. So there should be no free electromagnetic waves if Helmholtz's theory was right. So Hertz decided to try and see whether he could produce and detect electromagnetic waves, which would be a great triumph for Maxwell's theory, and definitively show that Helmholtz could, even if it didn't definitively show Maxwell was right, it would definitively show that Helmholtz was wrong. Now, Hertz understood the theory mathematically as well as anyone possibly could. He was an extraordinary mathematical physicist. He was also an extraordinary experimentalist. At the beginning of his search in the 1880s, he had zero clue about what kinds of physical systems could produce, if Maxwell's theory or something close to Maxwell's theory was right. He had zero clue about what physical systems would produce electromagnetic waves and what physical systems would absorb, or if you like, detect electromagnetic waves. He didn't know anything about what geometrical configurations of materials would do it. He didn't know what kinds of materials would do it. He had a rather deep understanding, the community did at the time, of, for instance, the interaction between the electromagnetic field and dielectrics, ordinary solids. But for instance, as he began trying to construct devices that would both reliably produce and detect electromagnetic waves, he did it based on his knowledge of kind of static interaction between the electromagnetic field and the dielectric, like this fake wood. But one of the many problems he faced was that the detection of electromagnetic wave would clearly have to take the form of the measurement of some kind of oscillatory motion in a detection device, something absorbing electromagnetic waves. But how could he distinguish between that oscillatory motion and other oscillatory motions that the solid, liquid, gas, whatever he was using, would presumably be experiencing from other causes? He had to have a really detailed understanding, even more detailed than they had at the time, of the interaction between the electromagnetic field and ordinary substances to do that. And he had to have a very deep understanding of how geometrical configurations of ordinary substances interacted with particular geometrical configurative solutions to the Maxwell equations. And it was this really wonderful dialectical process of he would build an instrument, do some experiments, things wouldn't quite work out. He'd go back to his theoretical model of the experiment and of the instrument, play around with that, have an idea for a new instrument, go and build a new instrument, didn't quite work out, he'd go back and rework the theoretical model. He kept on going back and forth between the theory and the laboratory. It took him several years until he finally came up with what we now call the dipole oscillator, and definitively showed that it could both produce and detect electromagnetic waves. I claim that until Hertz did that, electromagnetic waves were not part of the empirical content of Maxwell theory. I gave a talk last month at NYU, talk about going into the belly of the beast and bearding the lion, the metaphysical lions in their den, on this stuff. And I was discussing this example, and Kit Fine started pressing me. He's like, no, but Hertz knew the solutions to the equations. That's the empirical content. So he knew what electromagnetic waves were. He understood it perfectly. And all I could say was he couldn't use that mathematical knowledge to build something that would detect or produce electromagnetic waves. So in what sense can you possibly say he understood that the electromagnetic waves is part of Maxwell theory? If your understanding is completely sterile, doesn't allow you to actually get anything accomplished in the real world, it's not understanding. It's something that makes you feel good while you're lying in bed at night and congratulating yourself on how clever you are. which I'm sorry to say I feel is a lot of metaphysics. So, in the interest of time, because I'm going much more slowly than I had anticipated, so Enzo, the session is supposed to end at 12:30, is that right?
12:30, we have an hour.
Okay. Then there's so I think I will not go through the example of gravitational waves in any detail. I'll simply remark that I don't think it was really until the 1950s that gravitational waves really became part of the empirical content of general relativity, with the work of especially of Pirani and really pretty much Pirani. But if you're curious, I invite you to look at the slides or ask me over a glass of wine or something. Yeah, so this is all still about that. I will discuss black holes because that is relevant to what we're going to talk about later in the afternoon. So, in the formal theory of general relativity, the exact solutions we know for black hole spacetimes, essentially, at least for electrovac, ignoring things like Vaidya and stuff with matter in them, there's one family called the Kerr-Newman family, and subfamilies are Schwarzschild, Kerr, and Reisner-Nordstrom. So these are asymptotically flat solutions. They represent, if you like, the black hole as an isolated system. If you go infinitely far away from the black hole in the mathematical model, space-time becomes flat. It begins to look in some, speaking very crudely and inaccurately, but what the hell, it gets the idea across. Space-time begins to look Minkowskian, or if you like, Newtonian. These are the only exact solutions we know for isolated black holes. The no-hair theorems, in fact, tell us that they are the only solutions for isolated black holes, isolated asymptotically flat black holes. But you may wonder, well, you know, when we're studying Sagittarius A star, the supermassive black hole at the center of the Milky Way, it's not an isolated system. It's in the middle of a galaxy. There's stars swirling around it, which is actually how we discovered it in the first place. There's gas and nebula and ambient magnetic fields, and there's all kinds of crap going on. And it's certainly not the case that as you go infinitely far away from the center of the Milky Way, the universe becomes Minkowskian. And yet we use the Kerr model, the model of a rotating black hole, rotating isolated black hole. It's asymptotically flat mathematical model as an idealization in order to, when we're modeling Sagittarius A star for use in the Event Horizon Telescope, for modeling it to model binary black hole coalescing systems for the production of gravitational radiation as measured by LIGO-Virgo-Cagra collaboration. In fact, for many, if not most, if not all, theoretical applications in classical general relativity, most of astrophysics and pretty much all of cosmology, whenever black holes are relevant in cosmology, we use one of these asymptotically flat models to model a black hole, and it works unbelievably well. And we have a good understanding of why it works unbelievably well. Because, with respect to Sagittarius A star, Earth essentially is at future null infinity. And even though we don't feel like it most of the time, space around here is pretty flat and empty compared to Sagittarius A star. So it really is a good idealization to use, even though it seems rather extravagant to talk about an entirely empty space-time with one single black hole at the center as the model for this thing in the center of this really active, messy galaxy. But it works great. I feel like we have really, really good epistemic control over the use of that idealization. In semi-classical gravity, in black hole thermodynamics, we use the same idealization. Essentially, every single derivation of the Hawking effect uses a Schwarzschild Schwarzschild black hole or a collapsing body that settles down to Schwarzschild. But I don't think we actually have very good epistemic control over this idealization in this context. And in fact, one can argue, I think very compellingly, that it is exactly the illegitimate use of the idealization that leads to so many of the seemingly very deep and intractable problems in black hole thermodynamics, like the information loss paradox. So, in some cases, our theory of black holes, if you like, is under great control. And in some cases, I fear it is not under very good control at all. To paraphrase Jorge Luis Borges, física no escribe los primeros contactos de la realidad en matemáticas, sino su elaboración final en concepto. Physics does not write reality's initial context in mathematics, but rather its final elaboration in concepts. To understand why the use of Kerr or Schwarzschild is under control for use at the Event Horizon Telescope and LIGO, and understand why it may not be under control in studying the Hawking effect, is something you can't get from the mathematics. You really have to understand how the mathematics is applied in practice to understand why the one is unproblematic and the other is, to my mind, deeply problematic.
If so, how do you define or understand isolation in terms of black hole theory? When is something isolated? Is this more combined to information loss?
So, that's a really good and very hard question. I don't think that there is a single answer to that question that will apply equally well to all investigative contexts. What it means to be isolated for the purposes of the Event Horizon Telescope is the justification for using Kerr, the Kerr model, in constructing, in analyzing, structuring, and comparing the data that the Event Horizon Telescope constructs with the predictions of general relativity. What you really care about there are two kinds of isolation. You care about gravitational isolation, and you care about electromagnetic isolation. And it's, as these things go, relatively straightforward to show that the gravitational effects of everything around, everything in the neighborhood of Sagittarius A star is utterly negligible compared to Sagittarius A star's own self-gravity. And it's, again, but the electromagnetic isolation is a little more difficult because we really don't have a good understanding of the plasma physics of the accretion ring and even of the ambient background magnetic field that pervades the Milky Way. And so there's more uncertainty there about whether or not it makes sense to ignore those electromagnetic effects in modeling Sagittarius A star for the purposes of the Event Horizon Telescope than the gravitational effects. So it's exactly these kinds of things that you have to be able to think about and reason about in order to say, is this a justified idealization or not? But it's going to differ from case to case. In the case of the Hawking effect, one of the reasons why I think that treating the black hole as isolated may not in fact be a good idealization is partly because, for one thing, or at least the asymptotically flat part may not be a good idealization, because you actually want if you want the black hole to evaporate, it has to lose mass. If you want the black hole to lose mass, it has to radiate its mass away in Hawking radiation. And the way that you measure the decrease in mass is by the change in a quantity called the ADM mass, which is a global quantity in a relativistic spacetime. But if the ADM mass is changing non-negligibly, then that means that the Bondi mass is non-trivial. But that means your spacetime is not asymptotically flat. And so Is it close enough to being asymptotically flat that we can ignore that effect? Well, I don't think anyone knows because we don't understand the Hawking effect well enough to be able to say what effect, considering the what would change if we actually took the back reaction of the Hawking radiation at future null infinity into account and treated the space-time that we're modeling the Hawking effect in as not asymptotically flat, but actually as having non-trivial curvature at future null infinity. No one knows. I personally suspect that it's a bad idealization, but that's a long argument.
But that's the point, right?
Yeah.
And this also holds for global or local interpretations, I guess, for black holes.
Mm-hmm. That's right, yeah. Okay, so breakdown scales and the regime of applicability, one of my favorite topics. I love this shit. So Sheldon Glashow, the great 20th century physicist, one of the developers of the unified electroweak part of the standard model of particle physics, said, and I completely agree, a physical principle cannot be said to be true until it has been shown to be false and its envelope of applicability delineated. I love that. So I think it is appreciated that one must analyze and control for errors and selection and other biases in collecting and structuring and using empirical data. And especially as we collect it and analyze it and control for it in ever more sophisticated ways as experimental precision and resolution increase. This is a very serious problem in astrophysics and cosmology, where we're now starting to use computer simulations as part of empirical evidence, which is also done by actually at the LHC, at CERN, and in a lot of high energy physics. So, but it's perhaps not so widely recognized that theories and theoretical models, both in themselves and when used to structure and interpret data, require the analogous. We have to delimit when under what conditions, as applied to what systems, these theories or models are appropriate and adequate. And this is a really, really, really odd thing in physics that I would love to understand. I don't understand it at all. As far as I can tell, it's just a brute fact about our understanding of the physical world. I would really love to have someone explain to me whether this is just completely fortuitous, circumstantial accident, or whether it's telling us something very deep about the world. But for every physical theory that we have, it's characteristic of the kind of system that it treats that there is a set of scales at each of which all the theoretical quantities that the theory attributes to the system simultaneously lose definition. So, when I begin to shake the water and it becomes turbulent, all the quantities that Navier-Stokes attributes to it, fluid velocity flow, pressure, shear stress, they all lose definition at the same time. It happens with Maxwell fields. All the properties of Maxwell fields. Intensity, if it's an oscillatory solution, frequency, wavelength, polarization, they all break down at the same place when quantum effects become important. Every theory, insofar as it treats an appropriately unified kind of physical system, not only has a regime of applicability, but it has, in fact, a single unified one, bounded on all sides by scales characterized by the values of different combinations of its quantities. So I've already told you a few for Navier-Stokes, the definitions of pressure, fluid flow, viscosity, shear stress, break down at spatial and temporal scales a few orders of magnitude greater than the mean free path of the constituent molecules. But they also, all the quantities lose definition when the fluid enters a strong enough state of turbulence. And that is a scale that's independent of that, that's characterized by the mean free path of the molecules. It's important also to note, it's important to recognize that these scales aren't fixed once and for all. The regime of applicability of Navier-Stokes has increased dramatically over the past 150 years. If I remember correctly, Navier gave the first formulation in 1820, something like that, and Stokes did it in the 1850s, and then Stokes perfected it in the 1850s. And people, were using it immediately because it was just such a powerful and very elegant and beautiful theory. It gave us just unbelievably good predictions for classical fluids. But of course, the experimental technique back then, it was incredibly difficult to get precision that was smaller than probably a centimeter. Today we can probe fluids at scales of 10 to the minus 8 centimeters. So, and we can, back then the regime of applicability of Navier-Stokes was spatial scale a centimeter. Today it's 10 to the minus 5 centimeters. So the regime of applicability and the breakdown scales themselves are dynamic quantities. They evolve as our experimental prowess increases and as our theoretical prowess increases. Because just because you have an instrument that allows you to make, in some sense or other, measurements of a fluid at scales of 10 to the minus 5 centimeters, doesn't mean that you have the theoretical apparatus to use that data. You have to be able to build models of specific fluids in specific situations that represent the experiments that probe things at 10 to the minus 5 centimeters. So you have to have developments and improvements in both theory and experiment, almost always working in tandem. But that's what happens in science. And so, yeah, the regime of applicability and the breakdown scales tend to enlarge, improve, shrink, whatever actually happens, whichever direction is better over time. And in fact, this seems indeed to be one of the markers of a physical theory, the existence of a set of characteristic scales for its physical quantities, at each of which all the theory's physical quantities simultaneously lose definition, places where all the kinematically and dynamically relevant structures of the theory break down all at once, in the sense that the theory becomes inadequate for an appropriate treatment of any system beyond the determined boundaries. And although I think we perhaps naively tend to think of scales determined by spatial, temporal, and energetic quantities when considering how, why, and where theories break down in their capacities to provide sound representations of phenomena, any quantity in any theory can provide such a measure. So velocity provides a breakdown scale for Newtonian mechanics. Velocity, when something is moving at an appreciable velocity, speed of light, Newtonian mechanics isn't going to work anymore. Acceleration and scalar curvature provide different breakdown scales for various theories of gravity, such as GR. And no breakdown scale, moreover, can be a single number holding for all systems the theory treats. So, Navier-Stokes theory becomes inadequate for different fluids at different energy and spatial and temporal and energetic scales. If I tell you what the breakdown spatial length is for the water, it's going to be very different for glycerol, it's going to be very different for alcohol, it's going to be very different for air, it's going to be very different for everything that Navier-Stokes treats. And often it is not a bound on a single quantity, such as the value of energy, but that provides one. So classical Maxwell theory, breaks down when the ratio of the field's amplitude to its frequency approaches h bar. And nor is it ever the case that there is a single characteristic scale for each theory. So I've already told you some of the ways that Navier-Stokes theory breaks down. It breaks down when the theory is too viscous. When the fluid is too viscous, Navier-Stokes doesn't work for honey. And Navier-Stokes breaks down, over time scales comparable to equilibration time after a sharp disturbance. If I do this, the time it takes, if I try and make measurements on a much shorter scale than the time it takes the water to re-equilibrate after the shock, Navier-Stokes can't handle that. But then some things that I haven't mentioned yet, but that are really important and worth keeping in mind, that sometimes theories break down due to phenomena or behavior that is not actually representable in the theory itself. So, Navier-Stokes theory doesn't allow you to represent the electromagnetic field. It has no quantity or structure in it that allows you to give a representation of the Maxwell field. But if the ambient Maxwell field in this room were large enough so that the molecules in the water started to ionize and denature, then Navier-Stokes isn't going to work. Or if the water is hot enough that the loss of heat due to black body radiation is not negligible, then Navier-Stokes isn't going to work because it can't account for that loss of energy. But those aren't things that Navier-Stokes can represent. So breakdown scales, and that I think really makes incredibly vivid. I'll get it in a moment. I just want to finish this thought. That makes really, really vivid and clear, I think, that to understand the breakdown scale is never a purely theoretical endeavor. Theory by itself can never tell you the breakdown scales. It may tell you one or two. I mean, especially if you've constructed the theory to start with so as to accommodate the breakdown scale, which is essentially what effective field theories in condensed matter and quantum field theories do. They build in the breakdown scale when they're constructing the theory. But even there, that's only one part of the breakdown scale. There are many other ways that the theory can fail than the one that the effective field theory was constructed specifically to accommodate. So a theory can never by itself tell you when and where it's applicable and when and where it's not. That is something that can be learned only through empirical, experimental investigation. Wait, one of you.
Yeah, it's very interesting, and exactly what I wanted to point into. So that's the breakdown. It's not in the Navier-Stokes equation itself, but for a minute, taking the perspective from the Navier-Stokes, what makes it really break down? Isn't it then a computational limit that they don't have enough capacity to deal with it? Or, I mean, they also don't have a model for change in the fluids, right? They still would consider it being a fluid when you have the vortices, and they would still take the Laplacian demon perspective at it, right? They would say at some point it just cannot handle this amount of chaos anymore.
Right.
But in principle, they would say they could, right? With Navier.
So yeah, I mean, if you're talking about like the people in the mid-19th century, then yeah, I mean, in the mid-19th century, especially given the way that Newton's Principia dominated physics for 250 years up to that point, and Newton's theory of gravity was the exemplar of what a physical theory should be, and no one had any serious doubt whatsoever until the 1880s or 1890s that Newtonian theory might be wrong. The idea of when and where and how a theory might break down, if you really thought of it as a fundamental theory, just never occurred to people. But yeah, but when you do think about how, when, and where, and why a theory may break down, it may be for many different reasons. So if you truly believe you have a truly fundamental universal theory that covers absolutely every aspect of physical reality, then yeah, there won't be a breakdown scale. But I actually don't even think that's a cogent idea, personally. That's an interesting idea. I think that my own gut reaction to that, my initial reaction to that, is I think that one could possibly produce reasons and arguments that would be somewhat compelling, let's say, in favor of the idea that that you're not going to get this to the complete theory. But I don't think that we will ever be in a position. I think I'm too much of a skeptic to say that. I think it seems to me very unlikely that we will ever find ourselves in a position to make a absolutely ironclad, indubitable argument to that effect, because so much of what I'm saying about our knowledge of physical theories and what it takes to have confidence that one really has a theory under control is based on how physics has actually developed and where we are now, what our current epistemic state is. I'm too much of a mitigated, unremitting skeptic to say that it will always be impossible for us to make the kinds of arguments that you're making, or to have the kinds of knowledge that would allow us to make the kinds of arguments you're suggesting. It just seems to me, given our current epistemic state, very unlikely that we'll be there anytime soon, if ever. I think is what I would say.
The metaphorical analogy that I was thinking of course is the equivalent saying something, that there's something really powerful we can say in mathematics.
Yeah.
Can we correspondingly find something?
I mean, and again, the reason I'm skeptical about that is because so much of our knowledge of physics and our knowledge and our understanding of our knowledge in physics is based in very pragmatic issues, like the breakdown scale and the regime of applicability. And I mean, nothing in the idea of a breakdown scale or the regime of applicability tells you that it will always be relevant. It's just, so far, that's how things have worked. And if what we want to do is understand physics as it actually is, rather than physics as we may imagine it, then you work with what you have. So I think I've actually, I've remarked on the first point. I guess I should also say that just this is such an incredibly rich idea that I've been thinking about this, for years, and every once in a while I still come up with some new twists, some new example that's completely different from anything I've thought of before. So I mean, it's not only the case that that sometimes breakdown scales are determined by quantities or phenomena that's not even representable in the theory, but in fact sometimes you have to take account of the fact that approximations or idealizations that you're using to construct models of particular behavior, such as surface waves in fluid dynamics, have characteristic breakdown scales different from those of the material in which the phenomena manifest themselves. So if you want to understand the regime of applicability of a certain kind of model of surface waves in fluids, that's going to be very different than the breakdown scales for the theoretical treatment of the fluid itself. So it's a very, very rich idea that really repays thought. So a breakdown scale then is something like the following. It's a measure of, or a function of, or a relation among quantities such that when the joint state of the system and its environment imply that the values of some of the system's quantities do not satisfy the measure of functional relation, then the theory can no longer provide good models of the system. And as I've already remarked, but it's worth repeating, breakdown scales can never be determined by analysis of the formalism and theoretical machinery of the theory alone without input from knowledge acquired by experimentation in particular and empirical investigation in general. They are rather fixed by knowledge that one can gather only from investigations grounded in that part of the epistemic content of the theory not captured by the formalism by itself, largely in experimental and observational practice.
So the breakdown is a question of meaning, not of truth, in your approach.
Of meaning but not tools, did you say?
The breakdown, breakdown of certain theory, or certain model, is a question of meaning. That the variable of that model in this new regime are not applicable. Not this question of truth. That this theory is false. It's a new regime.
Right. No, I think that's exactly right. Yes, that's the way that I think about it. So I mean, think about the fact that since Navier-Stokes is in fact a continuum theory, it allows you, for instance, to make predictions about the behavior of water at scales of 10 to the minus 100 centimeters. Now we know that's nonsensical. There's no such thing, so far as we know, as fluids at scales of 10 to the minus 100 centimeters, or if there is, it's something we really don't know about. So, because Navier-Stokes is a continuum theory, predictions at scales of 10 to the minus 100 centimeters are necessarily encoded in all solutions to the theory. So, but we don't worry about that because we know that we can ignore all that shit. But it's not that the idea of pressure. I mean, the idea of pressure is meaningless, I would say, at scales of 10 to the minus 100 centimeters. The variable that represents pressure has no meaning in the theory when you're trying to apply it to scales of 10 to the minus 100 centimeters. But you don't worry about that. You just be careful to use and apply the theory only in the regimes where it makes sense. And yeah, so it's the one and the same quantity in one and the same model can be meaningful or not meaningful depending on what propositions you extract from the model.
Question? You say that the breakdown scales can never be determined by analysis of esempio, c'è la Landau in QED,
Mhm.
you can,
Mhm.
okay, so you can calculate the breakdown scale.
So that is one part of the breakdown scale. So I'm using this is my fault. I'm using the term breakdown scale ambiguously. I'm using it sometimes to refer to one specific measure, Landau pole, order of magnitude of mean free path of molecule, and I'm sometimes using it to refer to the collection of all of them together as characteristic of the entire theory. And the claim is that while you can, in fact, sometimes determine part of the global the aggregate breakdown scale from the theory itself, the Landau pole is a great example. The one I mentioned earlier, when you're constructing effective field theories in condensed matter or quantum field theory, you construct the theory from the start in such a way that you know at least part of the breakdown scale, because you constructed the theory to accommodate that. But I claim, not as a necessary a priori fact, just as a brute fact about physics as we know it, and that's how it's been all the way so far, that no theory by itself can allow you to determine the entire aggregate breakdown scale. So, but this still leaves a very important question, which is what does it mean to say that the theory cannot provide good models of systems outside its breakdown scales? And as I've already remarked, and as Enzo's question suggested, one of the most important markers is that the system's quantities lose unambiguous definition with respect to the theory's resources for modeling them. So for a Navier-Stokes fluid, for example, different sorts of thermometers that allow spatial discrimination on scales only a couple of orders of magnitude greater than the mean free path will record markedly different temperatures depending on characteristics of the joint system, the thermometer plus fluid, that one can ignore at larger scales. So the fine details of the fluid's convective flow around the thermometer in relation to the geometry of the thermometer itself, and even the transparency of thermometers to the fluid's particles. These are things that, by and large, you can ignore at larger scales, but as you approach scales where the interaction between the individual molecules in the thermometer, or at least groups of molecules on the thermometer, and the material and geometry of the thermometer become relevant, different quote-unquote thermometers will give you different readings for the temperature of the very same fluid in the very same conditions, which is a marker of the fact that at those scales and under those conditions, Navier-Stokes no longer works. You can't attribute unambiguously a temperature to the fluid. So, without knowledge of a theory's regime of applicability, and in particular when a given system of interest lies in its scope, we have no grounds whatsoever for trusting what the theory purports to say about the system. And this, by the way, I can't help remarking, even though it's one of the reasons why I truly loathe completely formal approaches to semantics and interpretation of theory is because they all rely on the idea of the set of systems that the theory applies to. But that is something that one can determine only pragmatically and experimentally. One has to assume the pragmatics before you can get to the formal semantics. But if you already know all that shit, what use is the formal semantics? Who cares? So, one can view physical theory to some degree as the rational reconstruction of experiment and data, as some formally minded philosophers seem to intend. One can also view theory to some degree as the codified articulation of a metaphysics and ontology, as other formally minded philosophers seem to intend. But as I hope to have convinced you by now, both can be so considered only to some degree, and neither one high enough to keep one warm on the long, dark, empty winter nights of the realized barrenness of one's reconstruction or articulation. Now that you have it in hand, what will you do with it? What problems will it solve or even illuminate? Ones of a purely formal character, no doubt. The contents of the concepts we deploy in our reasoning in physics and the consequences we draw from it The concepts whose interrelations constitute the claims we make in all of it are not exhausted by the mathematics nor by interpretations of the mathematics, much less by statements of what the mathematics represents. This is one of the reasons why, even though I was trained as a theoretical physicist, and in some ways I think people think a lot of my work is quite technical, I really don't like a lot of formal philosophy. The concepts are informed by all aspects of scientific practice, including the messiness of experimentation and the mushagas of observation, much of which cannot be captured by the mathematics, and much of that, when the mathematics is involved, cannot be clearly disentangled from the mathematics. So I think the appropriate methodology, especially when we're interested in questions of epistemology, which some people say I know there is a very strong and large and sizable and vocal community in philosophy that seems to believe that epistemology depends on metaphysics. I think that is completely ass backwards. I think the appropriate way to study scientific theories and physics philosophically is to treat matters as epistemological as far as possible, moving into metaphysics only so far as necessary, and then always grounding it in and constraining it by the knowledge and understanding one has acquired in conformity to the epistemological principles one works with. Now, I think that this is actually a pretty good place to stop to give time for a discussion. Before I jump into quantum gravity, which I guess I'll get to in the afternoon. But Enzo, how does that sound to you?
Yes, the preceding slide, this point, to stay for the most part of time in epistemology and not in metaphysics, is something that concerns when you have scientific aims or in general? Is a sort of forbidding to make metaphysics in absolute or only?
Well, my own opinion is that this pretty much always applies. So not only when thinking about physics or science, but also when thinking about philosophy itself. You know, when
Also in philosophy.
yeah.
Not in science.
Yeah. I mean, so you know, think about theories of scientific representation. You know, you have like Tarskian semantics gives you like a designative relation of representation. You know, possible world semantics gives you something like a depictive representation relation of representation. You know, something like a structuralist like Stephen French gives you something like a verisimilar relation of representation. But how on earth am I to understand what these relations are unless someone tells me, unless someone explains to me things like when they're appropriate, when they're adequate, what their breakdown scales are, when the concepts that are being used are applicable or inapplicable in a given context? Because I find it very hard to believe that, you know, if let's say it turns out that Tarski semantics or von Frassen's bet semantics is really the most fruitful, best way to go in trying to understand the empirical content of a theory and the semantics of the theory. Well, I find it really hard to believe that that's going to work, let's say, for quantum field theory and curved space-time for various reasons that are somewhat complicated. But then it's then incumbent on someone like von Frassen to tell me when, where, why, and how his account of scientific representation is appropriate and works, and when it's not. But I have no idea how to do that for that kind of theory.
So in a sense you are against naturalized metaphysics. The only possible function of naturalized metaphysics is to help science. Okay.
I am opposed to naturalized metaphysics. Yes, I love James Ladyman. He's wonderful. I cherish the moments when we get to hang out in a bar and drink beers and shoot the shit, and he's great. But when he tells me he's not a metaphysician, I just fucking laugh. I mean, come on. ontological structural realism is not a metaphysical position. Yeah. But I mean, I think it's important to note also. I think it's important for me to say that I'm not only opposed to naturalized metaphysics, I'm also opposed to naturalized epistemology, at least in its current state. I'm really with Carnap on this, not with Quine. It may be the case that if you really think about what a naturalized epistemology would be, it would have to be one that was grounded in something like cognitive science, in cognitive sciences and neuropsychology. Our knowledge of cognitive science and neuropsychology is so woefully barren and shallow that, I mean, we still don't even know if we have the right way of discriminating types of memories, much less whether we can model a scientist working in her laboratory and reasoning and arguing and comparing evidence. I mean, that's just total fucking bullshit. We are so far from being in a place where we can actually use science to ground epistemology, that the idea that we ever will be able to do it is at best an aspirational hope. And if we ever get there, great, let's use science to ground epistemology. But we are so far from that point that the claim that we should ground epistemology in science is at best fantasy, and at worst is unbelievably misleading and profoundly confusing. So it may be the case, Quine may be right, at some very deep level, there may be some continuity between the epistemology of the everyday world and the epistemology of science, and it's all grounded in empirical psychology and neuroscience and all that. But that's nothing remotely near our present epistemic state. And to pretend otherwise is to perpetuate really, really bad philosophy. So the kinds of things I'm doing, I think, are what one should worry about in trying to understand the epistemology of science. Nothing I mentioned is in any way treatable by cognitive science, by neuropsychology, by anything like that. We shouldn't pretend it is. This is not naturalized epistemology.
But what are you basing it on then? Just metaphysics?
God, I hope not. No, it's absolutely a fair question. I'm a pragmatist at heart. My heroes are Peirce and Carnap almost all philosophical questions boil down to semiotic, to understanding meaning and representation. And my analysis of the epistemology of physics is based on my own understanding of physics and based on my understanding of how theory and experiment work together in physics.
So I was thinking about habits while you were talking of.
Mm-hmm.
I was thinking of bringing up Peirce, but it's nice that you do now.
Mm-hmm.
But the Peirce in semiotics and Peirce himself is an attempt to naturalize, I would say, to some extent, a logic of reasoning or a form of thinking about that. But the Peircean way and his interpretation of habit, I mean, he explicitly, when he treats habits, he explicitly goes on describing them as not just conventional habits by speaking communities, but kind of goes deeper and says, okay, we have these habituating phenomena elsewhere in the natural world. So there's directly this, I would say, idea of basing the habit and the semiotic theory in something deeper. So, yeah, that seems then like that you're just taking a certain part of Peirce.
Well, sure. Just because Peirce is my hero doesn't mean I agree with everything the guy said.
But it's still kind of, where does it start?
Yeah. No, I mean, so first of all, I'm pretty sure that not everyone in this room is an expert on Peirce, so I don't want to go on a long Peirce exegesis. But I would love to over beer or something sometime. But I'll very quickly say that I think that one can detach a lot of Peirce's semiotic from the parts that seem to me of what really should be grounded in science, like the study of habit. That to me is clearly a part of empirical psychology. And I have hopes. I mean, there's places in some of Peirce's unpublished writing which has I'm sure you know is the overwhelming majority of Peirce's writing, where Peirce admits this and says, look, I'm talking about habits, but really this is something we need to study scientifically, and we still don't know enough about it yet. But he usually doesn't talk like that. And so I would say that I admire Peirce's spirit and a lot of the big ideas more than the fine details.
Okay, but then just so it's more interesting for everyone, let's leave out Peirce. But the question I'd still be interested in asking you, then it seems when you say, okay, we can't naturalize it, it seems more that you're pointing towards a, I think, very founded and well-reasoned critique of the current state of neuroscience and how much we can say in this regard, but then still kind of, I would say that how you do what you do, there's still a lot of there are a lot of like naturalizing tendencies, and there's a lot of reliance on history and a big reliance kind of on how theories have. So that there are a lot of still kind of scientific-like approaches that you employ in there.
Absolutely, I agree.
I agree in terms of the critique of neuroscience that doesn't allow us the full-fledged theory, but the methodology that you use to construct your epistemology still seems to have a lot of resonance now with many of the other scientific.
I absolutely agree, and I would be profoundly worried to the point of jettisoning all this stuff if it didn't. I mean, just because we can't base epistemology in neuroscience or cognitive science doesn't mean that when there are points of contact, they shouldn't be consistent with each other.
Yeah. Thank you.
I think that we can go to the difficult question. Until now, very easy question. Now,
okay.
Only because before and close to Erik. We have 15 minutes for difficult question before the break for lunch. I already posed my difficult question to Erik. Other people who want to ask something.
You think?
I don't think this is a difficult. Oh wow. I feel like it's still more of a clarification question. I'm not trying to challenge you.
That's cool.
Right. One of the rule of structural realists is there is a continuity in science, right? And structure captures that. Do you think that just specifically in terms of the breakdown scale, the theory that's after the previous theory should always have a lower breakdown scale, so it actually covers the bigger scale?
Yeah, no, not necessarily. Here's a great way to get free beers. If you're at a bar with a physicist, make a bet with them that it is not always the case that things that happen at scales much smaller than h bar have to be treated quantum mechanically. If you calculate the action, so if you use classical statistical Boltzmannian mechanics, to model the air in the room, say, and you calculate the action, the classical action, of the collision of two air molecules, where you use some reasonable size for the collision cross section, maybe 10 to the 2 times the molecular radius or something like that. The value of the classical action is about 10 to the minus 20 times, is 10 to the 20 times smaller than h bar. But we use classical statistical mechanics all the time, and it works great. So no, these things are always more. These things again there's almost never a single linear answer to these things. Things are just complicated and messy, and you have to figure them out.
Do you see yourself as in contrast with the structural realist? Because I don't necessarily see.
Absolutely.
Can you elaborate on that a little bit? Because I
Sure.
don't see it necessarily
I don't think anything I've said so far necessarily conflicts with it. So my dissatisfaction with not just structural realists, but structural approaches to things like this in general. I mean, I can maybe say a few things. It's not directly relevant to the lecture, but I'll very quickly. So I'm not going to work. So one of the common criticisms or problems attributed to structural realism, say, is to give a non-circular and substantive definition of structure. I'm not so worried about that. But it's rather to me that exactly because every theory has many different formulations, and it's very often the case, it's almost always the case, that there is either a total lack of isomorphism or even homomorphism between different structures in the various formulations of the theory. But even worse, in cases where you have different formulations and you can show, let's say, some isomorphism, and yet the things at either end of the isomorphism mean different things, then I just don't see how structuralism can be right. So I'll give you an example. So, you know, everything in classical physics has a Hamiltonian, basically everything has a Hamiltonian and a Lagrangian formulation, ignoring, let's say, dissipative stuff that doesn't have a Hamiltonian formulation. And we tend to think, so let's just say the simple harmonic oscillator, you know, pendulum. You get consider the Lagrangian formulation and the Hamiltonian formulation. So the Lagrangian is formulated on the tangent bundle of configuration space, and there's no natural symplectic structure on the tangent bundle. The Hamiltonian is formulated on the cotangent bundle of configuration space. There is a natural symplectic structure there. The natural symplectic structure is what you use to formulate Hamilton's equation. And the symplectic structure has a very natural interpretation, a very natural meaning. It encodes, among other things, conservation of energy. So part of the physical meaning of the symplectic structure in Hamiltonian mechanics is conservation of energy. In Lagrangian mechanics, if you give me and it's actually really important to notice that as what was implicit in what I just said, the symplectic structure in Hamiltonian mechanics is completely independent of the dynamics. It's fixed once and for all, entirely independent of the state of the system, of the actual dynamical evolution, of the value of the Hamiltonian, all that. It's just part of the brute kinematics of Hamiltonian mechanics. In Lagrangian mechanics, it turns out there's this beautiful theory of the geometry of tangent bundles, and even though tangent bundles don't have a symplectic structure, they have something called an almost tangent structure, which actually lies at the heart of the Euler-Lagrange equation, just like the symplectic structure lies at the heart of Hamilton's equation. And you use the almost tangent structure to formulate the Euler-Lagrange equation, although you never learn that in Mechanics 101, but that's really what you're doing. And it turns out that you can use the almost tangent structure if I give you a Lagrangian, and it's a regular Lagrangian. The almost tangent structure allows you to define a symplectic structure on the tangent bundle, but it's one that depends on the Lagrangian. And in fact, under the Legendre transform, that symplectic structure gets mapped to the Hamiltonian symplectic structure. But there are very profound differences in meaning between those two symplectic structures. In the Hamiltonian case, the symplectic structure is just part of the kinematics, it's not dynamical at all, and it encodes conservation of energy. In the Lagrangian case, the symplectic structure depends on the dynamics and does not encode conservation of energy. So I don't understand how you can be a structuralist when I give you the Lagrangian representation of a pendulum and the Hamiltonian representation of a pendulum, and I say, look, there are symplectic structures in each one. They're isomorphic, same structure, but they mean totally different things. I don't understand. If you can't explain something as basic as that to me, how two isomorphic structures in models of the same system can mean different things, then I don't think your position works.
Well,
One moment.
Yeah.
If there are other questions. Someone other questions from yes, okay? Sorry.
Yeah, it's about this priority relation between metaphysics and epistemology. So I'm not sure what to think myself about this question, but when I was in undergrad, I was presented with this argument for why the priority should be the other way around. I think it was by Williamson, and it goes like this. It was against a more Kantian conception, so not a Carnapian one, and it was something like the following. If you start by considering what the conditions for knowledge are in general, then, and what the methods in general are, then you'll kind of, you'll end up on a loop, as it were, because you'll also have to consider what the methods you use to investigate what the methods are, and so on, and you'll basically get stuck, and you won't start studying whatever you want to study, and you'll basically only study epistemology and won't get into contact with the world, as it were. Yeah, something like that. And I was wondering what you think about an argument like that.
Oh, that's a great question. So to me, the reason why that kind of argument doesn't make an impact on me is because I think that it rests on a completely illegitimate conception of knowledge. I mean, I basically blame Descartes for almost everything that's wrong in philosophy, and for almost everything that's wrong in maybe the wider Western world. The idea that knowledge should be that certainty should be part of the conception of knowledge to me is just unbelievably stupid. It certainly wasn't part of the Greeks, the ancient Greeks' conception of knowledge. It wasn't part of most medieval thinkers' conception of knowledge. And the idea that one can know only if one is absolutely certain, that means we'll never know anything. We'll never be absolutely certain of anything. Or I would perhaps better prefer to say that sense of absolute certainty that is required by this picture of knowledge it's a fantasy. You work with what you have. And yeah, in some sense, there's always a regress. Yeah, big deal. Right now, I'm going to pause at this point in the Heraclitean flux and take my stand with the resources I have and make what advances I can. And if you want to go and worry about certainty and think about your metaphysics and say that your metaphysics is what gives you certainty, go and have fun, dude, but I'm just not going to care in the slightest, because that to me is so epistemically full of bullshit that I just cannot bring myself to care about it. So yeah, short answer, blame Descartes for everything. The most epistemically interesting states have nothing to do with absolute certainty.
We have time for another question. Yes, go ahead.
Probably not a hard question.
Okay. I'm not sure if you said this before when you were talking about epistemic control, and I think I'm still not totally sure what that is.
Hey, join the club.
Right, but I think that's a really interesting thing. But I'm wondering if you have a more detailed account of how epistemic control relates to progress in science. First thing that comes to mind is like Alex Bird's account of the accumulation of scientific knowledge, which I don't think is probably the right account. But epistemic control looks like pretty fluid, like it comes and goes. I'm wondering if you could even have it by accident or something. So yeah, I'm wondering, how do I know if I'm making progress in science based on having some kind of epistemic control?
That's a really nice question. And the short answer is no. I don't have well worked out views on that. I think it's a very important question, and I would love to have well worked out views on it, but I don't yet. It's something I plan to think on. I mean, I think to my mind, probably the person I can think of whose work would be most sympathetic, would be most useful for me, and that my work would have most kind of consonance with, would be Deborah Mayo and Lydia Patton. And Deborah's picture of error and uncertainty as being the driver, as being in large part the drivers of knowledge, and Lydia's conception of iteration and looking for failure points. I think that those would really, that if I were going to try and work up an account of that, I think I would probably start there.
Yeah.
But I think it's a great question.
Yeah, super. I think epistemic control might be like more useful for thinking about progress than like some of the other notions that we have. So yeah, I think it's cool.
I hope so.
Yeah.
Another question? But we have 5 minutes, okay?
Yeah, so sort of just more to ask your opinion on this. Like, it seems to me like that this sort of statement about understanding the relationship between epistemology and metaphysics is like fits very nicely with the literature on philosophy of gauge. So essentially you have some quantity you want to see, sort of like the main question is posed as to be something like, is this quantity real in some sense? What's going on there? But like, it's always sort of a surrogate for like an epistemological question, which lurks behind, and it's sort of recognized as that, it seems to me, in the literature. So sort of, do you think like that could be sort of one part of the philosophy debate, but which goes along sort of this line of thought?
I think that's right. So I've had some interesting conversations with Enrique Gomez and Sean Gribb about very similar points. I don't know whether you're familiar with their work on gauge, but I think that they're doing probably some of the best work around today on trying to understand gauge theories. And yeah, they made a very similar point to me, and it sounds right to me. But I haven't had the time or the resources to sit down and think about it seriously yet. But I plan to, when in all my free spare time. I'm sorry, I don't have a more detailed answer for you.